Okay, and we are live. All right. I'm just gonna check. Okay, close this. Okay, so welcome everyone to our second series of the A-level revision series, and today we'll be discussing about chemistry. So we have two presenters today, Rehaan and Sophie, who are also both part of our mentoring scheme in In2MedSchool. And our moderators today will be Thea and I, and we will be basically handing out the Slido and all of your questions at the end as well. So if you are not a mentee in our mentoring program, please do sign up, as we accept year 12 and year 13s, and we have now created a form where year 11s are also available to sign up as well. Next slide, please. So who are we and what do we do? In2MedSchool consists of more than 2,500 student mentors from all over the UK, offering free mentoring sessions to disadvantaged year 12 and year 13 prospective medical students. We offer free one-to-one mentoring sessions, online webinars, and many educational resources to nail your medical school application. And you can also find all our resources on our website, www.in2medschool.com. And besides that, we now have a few new sponsors as well. So Medical Protection, MDU, and Medify are sponsoring all our events from now on. And they will be contributing to our resources that we would then be able to get for all of you as well. So now just to go through the usual webinar etiquettes. So appropriate usage of the chat and the Q&A function. The YouTube chat has been disabled, and you're able to send your questions on Slido. We will give you the code in a minute. Any inappropriate questions will not be addressed, so please be professional and kind to our volunteers. Send your questions throughout the webinar. There will be a Q&A session at the end of the webinar, as well as a mini Q&A session after the section 1 delivered by Rehaan later. This webinar is live on YouTube and will stay on our channel for you to watch at a later date. A certificate of attendance will be sent out once you have completed our feedback form at the end as well. And just to specify that the views expressed by our speakers involved in our events are entirely of their own opinions and accounts of personal experiences. And they do not represent the views of any university and do not necessarily reflect the official policy or position that In2MedSchool holds. And In2MedSchool has no affiliation to any university. And the next slide. So this is the Slido code. If you just go to Slido's website and you key in this code at a hashtag at the top of the page, you can then insert your questions in, and we will be moderating them as well throughout the whole webinar. Okay, and can we have the next slide? All right, so now I will pass on to our first speaker of the day, Rehaan.
Thank you very much. So, hi everyone, my name is Rehaan. I'm a second year medical student at Newcastle University. I'm also the regional head for Newcastle University, and I am one of the 3 teaching education officers for In2MedSchool. So today I'm going to talk to you for quite a while. Well, I'm going to try and keep it as close as I can to the time, but there is a lot of information to cover, and we are going to go at quite a fast pace. But just before we sort of get into it, just some quick notes about the event. So this is for my section on organic chemistry and also Sophie's section, who will be doing physical and inorganic chemistry. We're going to aim for about 40 minutes for these sections, and because of the very limited amount of time we have, we can only cover sort of very specific and what we think are, the most important or the most challenging high yield concepts, if you like. We're not going to be teaching much theory, rather we'll be giving you a lot of exam practice and questions and application questions and tips and hints and other ways to sort of go about. And it will be a really good idea for you to have some paper, a pen, pencil, calculator, some sort of data sheet or your textbook, because that will have the data sheet on it, and then the periodic table, because you will need to use those things. We've also emailed you out the booklet, which has all the questions in. So there's 2 booklets, one for section 1 and 2. So please have a copy of the booklet as well, because they contain the questions, and then we'll go through them and you'll get the answers to these after we've done the event. So In terms of what I'm going to talk through, again, like I said, can't do everything, but I'm going to focus on mechanisms mainly, and I will be going through sort of lots of the key synthesis reactions, if you like, okay? So mechanisms, synthesis reactions, these are the topics we're going to be doing. So we're going to be doing all the key mechanisms. We'll do a little bit on esters, some Pront and NMR questions, and then some challenging synthesis questions that I've made, okay? So starting off with the bromination of methane. Okay, so this is a free radical substitution reaction. Okay, so a free radical is basically just an unpaired electron on some sort of atom. Okay, so they're very, very reactive as a result of that. And then there's different types of reactions you need to know. So one of them, for example, is the bromination of methane. And they have different steps: initiation, propagation, and termination. So the first step is the initiation of the reaction, and that effectively involves the use of UV light. So UV light breaks down the bromine. Remember, these are the halogens, and they come as paired, they're paired halogens. It breaks down the diatomic bromine into two bromine free radicals. Okay, so these are very reactive and will go on to then cause these substitution reactions. Now we're going to look at adding methane into the mix. So if we add methane, which is CH4, okay, so the CH4 is going to react with one of the bromine radicals from there. Okay, so nothing challenging about that so far. What's interesting is this next part of the reaction here. So when methane reacts with bromine, it will form this radical here. So we'll have a radical on the carbon and hydrogen bromide. And if you just think about what's happening in the reaction, it makes sense. So the easiest thing with organic chemistry is to actually, rather than sit down and memorize all these reactions and, get in your head about them, is to understand why they happen. Because if you understand why they happen, you can apply your knowledge and it'll be easy for you to remember. So the bromine radical here is going to come along and basically take one of the hydrogens from the methane molecule to then form hydrogen bromide. Now, if you think, right, 4 there, it's taken 1, 4 minus 1, that's 3. Wow, rather magically, there's only 3 there. Okay, it's really easy. It makes sense if you think through the steps logically. And obviously, because carbon has lost one of its atoms, and its shared bond, its covalent bond, it will have a free radical there. And then what happens next is, well, this free radical, again, is very reactive. So it's going to go ahead and react with the initial bromine, so at the start of the reaction. So radical plus bromine. And this time we're going to form CH3Br, which is bromomethane, and a bromine radical. Again, this makes sense. One of the bromines is now going to go here to the carbon. The hydrogens aren't changed in this step. Only the bromine is going to the carbon because, again, the radical is on the carbon. And then what we left with, well, if we take one of the bromines from there, we've only got 1 bromine left. And then always check if your equation balances. And yes, it does. Okay, I've got 2 bromines here, 2 bromines here, 1 bromine there, 1 bromine there. And then finally, we have the termination steps. So if I just get rid of the drawings. Oh, sorry. These are the termination steps. So the termination reaction in any free radical substitution reaction is effectively the joining of any 2 free radicals. So the 2 bromine radicals coming together will end the reaction. And that will end the reaction, and that will end the reaction. Okay? However, the reaction does not completely end despite the termination steps. This is where there's a potential for the reaction to end. So if we want to make bromomethane, if that is our plan, okay, that's the product we want, that's great. And then we need to obviously try and stop the reaction here and take that out. But because these are sort of all gases and they're all reacting in a chamber, it's very unlikely that you will just get bromomethane being formed, and rather you'll get a mixture of products. And that is known as further substitution. Because if you look at the structure of CH3Br, it has more hydrogens left that can be substituted for bromine. So going back again, if you just think the steps, so CH3Br is going to go ahead and react with another radical. That is then going to form CH2Br plus HBr. And again, why is it that? Because look, one of the hydrogens has gone from the CH3Br and joined with the bromine. So the next step of the reaction is taking the radical and reacting it again with the Br2. So it's the same steps really, it's making logical sense. And then that will again, this time form 2 bromomethane. Or dibromomethane and a bromine radical. And then this will continue to happen. There'll be continuous further substitution until we get to this compound here. And the reason why the reaction ends with, having 4 lots of the bromines, because there's no more hydrogens left on the carbon for it to be substituted with. Okay, so obviously that all makes sense. So I want you to just have a quick think now. Now, the ozone depletion reaction is a little bit different, but I'm just going to give you a couple of seconds to think. Think back to what we did think. What would you think is the initiation step? Remember, initiation is the production of the radicals. So think, how can this compound here, CCl2F2, form 2 chlorines? Just have a quick think, then I'll go through the answers. Okay, so there's our Cl2F2. So again, like we said, we're going to form the chlorine radical, okay? So it's just going to, again, use UV light to split the reaction, and we get the chlorine radical left at the end, okay? And then this structure there. And if we look at propagation 1, now this time ozone, remember, is O3. So it's going to react with ozone. So the O3 is going to react with the chlorine from here. Right, so again, let's talk through the steps. So chlorine radical plus ozone is then going to form O2 and O. This makes perfect sense because look, that chlorine has taken one of the oxygens, so we're left with 2, and there's no oxygen there. And always check with these reactions whether they balance. If they balance, you are on the right lines. 3 oxygens here, 2 add 1, 3 oxygens there. 1 chlorine there, 1 chlorine there. Great, I'm probably correct. Right, now the next step, which is the second propagation step, is a step that students often find difficult. But again, it's just because it makes sense if you think about it, and it's just because this sort of structure here confuses people. But again, there's nothing too difficult about that. So we're taking the CLO from there, right? Again, nothing hard there. We're reacting it with this O here. Now, this technically should have a radical on it, but because it's stable, we don't put that. So the way in which we denote this sort of structure is without the radical. So the CLO just reacts with O, but it is a radical, to then form the Cl radical and O2. And again, that makes sense. So the 2 oxygens are coming together to form O2, and then the Cl is being left. Now, obviously, the Cl is now a radical, and because of the nature of these ozone depletion reactions, we reform the radical at the end. There is no termination like there was in the alkane free radical substitution reactions, okay? Because we reform the radical every time so it can deplete the ozone again. So again, this step can now go back and happen again. More chlorine can deplete the ozone further with O3, and obviously that is why we have, the risks of ozone depletion. Okay, so I hope that made a bit of sense. It is a bit complicated to understand, especially if we just sort of yell it at you, but if you take the time to look through the steps, it does make sense. So there's the nitrogen oxide reaction as well, which is the exact same principle as this. So I'm going to leave this to do for yourself, just for time's sake, and then obviously you'll get the answers as well. Okay, so again, just a quick note on why there's no termination. These radicals act as homogeneous catalysts, meaning they are constantly regenerated at the end, therefore causing further depletion of the ozone. So all that basically means is we are going to continuously reform those radicals to, again, continuously do propagation 1. So I'll stop speaking now. I'm sure you'll appreciate that. So there's 2 multiple choice questions. I'm just going to give you 20 seconds really because they're quite easy. Or have a look at this question, and then there's the one after that, and then we'll talk through the answers. Okay, so these are in your booklet as well, but take a look at this question here. Okay, and then the answer to this question is 1-iodobutane. And the reason for this is you basically need to know the rule that as you go down the halogens, there's a change in the strength of the carbon-halogen bond. So the iodobutane has the fastest rate of reaction because this bond is the weakest, because it has the least bond enthalpy, so it needs the least amount of heat energy to break the reaction, so it happens at the quickest pace. Okay, try the next question. Okay, the answer to this question is D. The carbon fluorine is the strongest carbon halogen bond because it has the most amount of bond enthalpy. It's also highly electronegative and all that. So again, it's a similar concept to the question we just did before, right? Great. So fluoroalkanes are the least reactive. The iodoalkanes, if you like, are the most reactive because they have the least bond enthalpy. So that's just a rule that you need to remember. Okay, so now I'm going to leave you with this question for a second, and this is another substitution type of question, but a bit harder that I've made. So have a read of this and we'll go through the answers. Okay, so you need to draw the skeletal formula of the organic product formed from the complete endpoint substitution of 2-chloropropanoic acid with chlorine. That sounds very overtly complicated, but believe me, it is not as hard as it seems. So let's take it step by step. Endpoint substitution means it can't be substituted anymore, so we must lose all the hydrogens. And it's going to be 2-chloropropanoic acid with chlorine. Okay, so I'm going to start off by drawing 2-chloropropanoic acid. Okay, skeletal formula, that's fine. So 1, 2, 3, these are 3 carbons here, and propanoic acid means that it is a carboxylic acid, so we're going to have an OH there. Sorry, excuse my horrendous drawing, and then O there. 2-chloro, meaning on the second carbon, there's a chlorine. So this is the first carbon, this is the second carbon. We name from the functional group, not this side. Unless there is no functional group, then it doesn't matter. So this is what this looks like. That's 2-chloropropanoic acid, right? And this is going to now be reacted with chlorine, and it's going to make a complete endpoint substitution reaction. So now we're going to chuck chlorine into the mix. So think, where are the hydrogens? Because they are what are going to be substituted. Well, there's a hydrogen here on this carbon, because every carbon forms 4 bonds. So obviously there's another bond there with a hydrogen. And there's a hydrogen here, and a hydrogen here, and a hydrogen here, right? At the end of the chain. So this is going to have chlorine. This is going to have chlorine. This is going to have chlorine. And lastly, this will have chlorine. Okay, nothing complicated about that. All you've done is remove the hydrogens for a Cl. And you know that's just the basic concept. It's substitution. You substitute something for another, and that is the answer. Okay, great. So let's crack on. Now we're going to look at electrophilic and nucleophilic addition reactions and so on. So an electrophile is an atom or group of atoms that are attracted to an electron-rich center where it accepts a pair of electrons. So these are generally involved in alkane reactions and things like benzene, etc., because there's an electron-rich center there. And nucleophiles are an atom or group of atoms attracting an electron-deficient carbon atom where it donates a pair of electrons. So this is more involving where carbon has been removed of its electrons, where it's sort of bonded to something like a halogen, if you like. So something that's taken the electrons from it. So electrophilic addition, cyclohexene, which is this compound here, is reacted with bromine to prepare compound F, okay? And basically you need to draw the mechanism. So you're going to be reacting. So you can read through this part, but this part's not really too relevant for this question. So what you're being asked to do is react cyclohexene with Br2. Okay? And this is an electrophilic addition reaction. To try and think, you can try and remember what the steps are. I'll give you a clue. So you have the 2, that's supposed to be a B, but that will not be a B. But you've got bromine and bromine. So this is the reaction we're going on about if you're not too sure. And then it effectively involves the movement of the electrons from here and down to here. Okay, so try and have a go at completing the rest of the steps. I've given you a bit of a head start, and then we'll go through the answer in a minute. Okay, just show you the answer just because of time. So, like I said, this is what we were trying to get at here. So, you can draw it with the carbons like that's showing the double bond, or you can draw it all skeletally. I prefer this way just because it looks a bit neater, but you can do that. However, with the new mark schemes, you're best to be careful, and I think they prefer this method here, with it all being skeletal. So, the electrons from here go to the bromine, and then from this one, they go to here. So this is an example of homolytic fusion. Sorry, this is an example of heterolytic fusion because one of them is taking more of them. So we are going to have delta negative on the bromine and delta positive here. So we form a partial dipole. The reason why this is delta negative is because this bromine has pulled the electrons in this bond towards it, making sort of the cloud of electron charge around that. So it's going to be delta negative, it's going to be delta positive. Then that is the structure of the product because both of the bromines will go ahead and replace sort of be added on to this reaction here. Oh, sorry. So we're going to now move on nucleophilic substitution. So try this question here. This is allyl bromide. This is a bit of an application question because you don't learn about allyl compounds in most of the specifications, but try and have a look at this reaction here. Just give you a couple more seconds. Sorry, the time is so tight. Right, so we'll move on. Okay, so allyl bromide. First step is actually drawing what this thing looks like. So you haven't seen allyl compounds, like I said. I can't move the slide for some reason. Hang on. There we go. No, too far ahead. Sorry about that. So allyl bromide. This is kind of the structure we're looking at. The key thing with this question really is what they're testing is whether you understand how nucleophiles work. Because a lot of people, when I read the examiner's report, started having the OH attacking here, which is not correct. Because remember, the definition of a nucleophile is it's attracted to an electron-deficient carbon atom, not an electron-rich center, because that is an electrophile. So a lot of people made the mistake of doing this, and this was done deliberately, I'm assuming from the examiners, is because they wanted to test whether you understood what a nucleophile was. So once you've got over that hurdle, everything else is incredibly easy. So you've got the OH with the 2 electrons there. That's attracted to the electron deficient carbon atom. It's deficient because this bromine is more electronegative, so it's pulled the electrons towards it, making it delta negative, and that's delta positive. And the electrons here attract to the positive charge there, and it substitutes it. So we're substituting the bromine, and we basically get an alcohol being formed. Okay, nice and easy. So electrophilic substitution reactions involve benzene. So this question would like you to outline the mechanism to form P. So this is a bit different because they've given you the answer and you've got to go back effectively and see how you formed it. And the hardest thing with this question really is to be able to identify what the electrophile looks like. Okay, so I think for this one, we're just going to go to the answers. So in terms of identification of what the electrophile looks like, this is what the electrophile looks like. So based on the structure, you've got to be able to extract that this is what it was, and remembering that it was a carbocation with a positive charge there, okay? And the actual mechanism you need to remember as well. So what happens is the ring, so this is the electron P cloud, will go ahead and attack this positive charge on the carbon, because obviously negative electrons positive there. And then that will form a bond. So we've done that part. And then the hydrogen, because all of these obviously have hydrogen, will be donated into the ring. And then we have this horseshoe shape there. And then the hydrogen collapses, and then the hydrogen, so we have an additional step, which isn't on here, but this is what the final step would be. The hydrogen is substituted out in replace for this, okay? So make sure you remember the concepts of benzene and why we have this ring, why there's only one hydrogen each rather than 2 hydrogens, because remember, each of the carbons are donating an electron in their p orbital into the shell, into the structure here, okay? So they only have 3 bonds, the carbons, rather than 4 as we're used to. Right, moving on. So now this is the nucleophilic addition questions. This is on the A level rather than AS. So have a look at this one. This is another application type of one. So okay, remember what nucleophile is, think where's it going, and try to use logic. You've got the end structure, so really it's not too bad. But just think we're going to be breaking this bond, obviously, because that's the difference. We aren't affecting the chlorines, but we are breaking this carbon bond here. Okay, so think, how would the mechanism look like for that? I'll just give you a few seconds to think, and then we'll go through the answer. Okay, I think that was probably not long enough, but we'll have a look. So this one's quite a fun question. Let me just get the pen tool. So again, it's testing whether you actually understand the definition of a nucleophile. So again, we're not taking it to this carbon. Okay, it does go to an electron deficient carbon atom, but not this carbon. It goes to this carbon because we need to break the double bond. So the 2 sort of lone pairs of electron there are attracted to this electron deficient carbon atom. Again, why is this deficient? Because it's bonded to oxygen. Oxygen is more electronegative, so it's pulled the electrons in the double bond towards itself. So we have delta positive there, delta negative there. This is going to attract to the delta positive carbon. Then obviously, because it's gone there, this has formed a bond. Yeah, that makes complete sense because it's literally just gone there. And now we've broken this double bond because this pulled the electrons towards it. So we just have this negatively charged oxygen there. And the key thing to remember with these reactions is that they will occur in an aqueous solution, which is where this comes from. Okay, so this is the step. So it's this part here that people find difficult, and more specifically, the water. But all it is just the electrons from the oxygen will be sent to the hydrogen, which will then send it to the oxygen here, okay? Because I'm going this, and it's more electronegative, so it will pull the electrons towards it. Okay, so here is another fun nucleophilic addition question. So have a look at this one. Okay, so I think if we just go, so this is what the answer to the question was. I think I'll talk through how we actually get to this point first, rather than moving on. So we've got this structure here, diphenyl ethanedione, which looks a bit horrific. And the question is asking you to draw a displayed formula to show the structure of the organic compound or organic product that will be formed by reducing this with excess NaB4H, which is sodium tetrahydroborate. So you should be able to recall from your lectures that, sorry, not lectures, lessons. I'm in uni. You should be able to recall from your lessons instead that sodium tetrahydroborate is used in reduction reactions involving sort of aldehydes and ketones. So really, this is just, if you look at the name OWN, this is just a ketone. So the ketone will basically go from being a ketone back to being a alcohol, and that's all really that you need to draw. There's nothing too complicated there, and that's all you have to draw. And it is only 1 mark in all fairness, but a lot of people struggle with this question for some reason. All you're doing is going from this to this. So this is what I mean by application. If you had just memorized the basic NaB4H reactions with any aldehyde, like a normal ketone or normal aldehyde without a benzene ring, you'd probably be fine with it. But when you are thrown someone like this, again, it's application, but nothing happens with the ring. You're just focus on what groups are reacting, and then obviously going to form the OH there. And have a think about what the name of this structure will be. Okay, so we're now going to move on to esters. Esters are quite fun. That's a big topic as well in A-level chemistry. I remember when I was doing it, there was just so many ways to make esters, and I couldn't keep up with how many different ways there are. And then something that was quite common in exams is hydrolysis of esters. And there's 2 ways you can break down esters. One is with acid hydrolysis, and one's with alkaline hydrolysis, so using sodium hydroxide rather than sort of an acid catalyst and water. So we've got enalapril, which is actually a drug as well. I can't remember what drug. I think it might be an ACE inhibitor. Why am I making that up? Anyway, it doesn't matter. So enalapril, Chalmers might know actually. Enalapril is broken down by the acid hydrolysis. So have a look at this and try and think. Well, the key thing with this is think about how it was made and then what you'd be left with if you went back to the reactants. So have a look at where the bonds are. That's what to focus on. So look, you've got an ester bond there. That will potentially break. Yeah, you've got this amide thing. Amide, sorry. You've got an amide thing going on here. That will probably break. You've got the amine there. So just have a think, the functional groups, and try and draw out what you think what the product of the reaction would be. It was an ACE inhibitor, so that's great. I managed to get that right. I did this right at the start of last year, so I'm happy with that. Like ramipril, yeah, exactly. Okay, so let's move on. Thank you, everyone. So the key thing to watch with the ester questions is the nitrogen charges. I'll talk about more of that in a second. So let's actually have a look at what bonds have been broken. So we are left with the ethanol chain. Okay, so if you know what I'm going to do, I'm going to keep flicking back and forth actually. So this here, if I get this, okay. So this is this, yeah? Very easy to see because we've broken that bond there. If we look at this one here, so this is proline, which is just amino acid. So this becomes NH2 plus. So if we have a look, we've broken this here. Okay, so the C double bond OH is fine, and then this has been broken, and then the H2 plus is on there, and we'll look at why it's 2 plus in a second. Then if we look back the rest of the chains, obviously if we break this bond here, what will we be left with? OH obviously, because it's a carboxylic acid, and there's the rest of the chain. And then again, we broke this one here, so a H goes there. So effectively, for the last mark, which people find the most complicated, just think where you've broken the bonds and where the H will be. So again, here we'll have a H, yeah? That is supposed to be a H. And then here we'll have OH, okay? So get rid of that, moving on. And then the remaining fragment of NH or NH2. So the key point I'm trying to make here is the nitrogen charges. So even though, so if we look at proline again, even though it was N there, it becomes NH2 plus rather than NH. NH2 plus is more correct because you have to remember this fact here, nitrogen makes 3 bonds. So obviously it will be protonated because of the acidic conditions, but remember it makes 3 bonds, so it will be completely protonated. So because we're using an acid catalyst, it's H plus, so that's where it gets the positive charge from, hence why the nitrogens will be protonated. So again, if we go back here, the NH will now become NH2 plus, okay, because of the excess hydrogen. This will not be NH3 plus because this has already made its 3 bonds, whereas this one will, rather than NH plus, it will be NH2 plus because it will need to make all 3 bonds, okay? So I hope that makes sense. I've tried to explain it as best as I can, but NH2 plus here, because it already has its bonds, and NH2 plus here rather than NH plus because it needs to make all 3. And where it gets the charge from is the acidic conditions. So this is another ester question. I think we'll just talk through this one instead. This is a bit of a weird one I found, just because I think this question was a bit weird. But it's going on about natural shampoo, and you're like, right, blah, 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 who cares? So you've got this weird looking structure here, which seems quite fun. So it's a type of reaction that could break down the sorbitin monolaurate when it is washed down into drains in rivers, and explain your answer and state the type of organic product formed. So again, hydrolysis reaction. So most likely, again, you can just use acid hydrolysis to break that down. Suggests one of the reasons why detergents such as sorbitin monolaurate are regarded as environmentally friendly. This question is just a bit weird, but probably because it's made from plants. But again, it's a weird question to be asking, really, but they like to ask weird stuff like that. So because it's made of plants, it's more renewable. So if we have a look at the mark scheme, hydrolysis, because it's an ester and it's broken down to form an alcohol and carboxylic acid / salt, or do the equation for the reaction. This is an old spec question, like a really old question. I think in the new spec, they would definitely ask you to draw this reaction out instead. So make sure you are confident in doing that and do that in your own time after this section. Sorbitin monolaurate, the reason why it is environmentally friendly is because it's made from plants, so it's a renewable source, so not based on crude oil. Or again, weirdy question, bit of a weirdy, wordy, how science works type of question. Okay, so now we're going to go on to protein NMR. Now, I really like protein NMR, but I think people find this the bane of existence for A-level chemistry. But I'll go through my sort of top tips with this and my approach to this sort of briefly, and then you can practice. So firstly, it's important that you have a method that actually works. So people, i.e. me, often the way we went about this was drawing a table. So you'd have a table with headings, sort of environment, structure, ppm, proton number, and then go through, label the spectra with like A, B, C, and D, and that's relevant to the environment in the table, and then add in, the ppm that you see on the graph or whatever the proton number is. Focus on identifying the environments first and the big structures, etc., and then work out the little stuff. Always use the proton numbers because they will tell you so much, and the splitting pattern is the most useful thing. And it's important to know what it means and what it looks like on the actual spectra itself. Remember, the splitting patterns is in reference to the neighboring adjacent protons of that carbon and not the carbon itself because of the n+1 rule. So it's the adjacent carbon, so it will tell you about the neighbor, not itself. You get most marks actually for the explanation, and then even if you don't get the structure, that's fine, as long as you write up and interpret the spectra, and everyone can do that. And then just have a go at drawing something at the end, try not to just leave it completely blank. Okay, so I'm going to sort of talk through my approach with this. So we've got a molecule here. First step is to identify the protein environments. So I can already see that we've got 1, 2, 3, 4 carbons. This is butane, it's alcohol, this is butanol. So what are the different protein environments I can see? Well, these are all the protein environments I can see. This is one environment. This is an environment. This is an environment. This is an environment. Because if we think about the structure of this, if it lets me change to the pen tool, that is. Hang on, give me a second. Right, I don't think it's working. I think my Zoom is crashed.
Does it crash?
Yeah, 1 second. Can you like take back control and I'll, hang on, it's back now. Oh, can you see it again?
Yeah, it's up here.
That's fine. Right, sorry about that, everyone. Okay, so let's carry on. So as I was saying, first thing is to really just look at the hydrogen. So I'm just going to do them as dots. So again, there's a hydrogen here, a hydrogen here, and a hydrogen here, hydrogen here, hydrogen here, hydrogen, 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 and then obviously hydrogen. So with protein environments, you've got to look at each sort of carbon. I think of them as like little houses, if you like. So compare one house with the other house. So if we look at the first carbon house here, this has got 3. Do any of the other carbon houses have 3 hydrogens in them? No. So this is going to be its own environment. And then the next one, now you've got to look at the neighbor. So its neighboring carbon has 3, but its other neighbor has 2. So that's a separate environment. And this is a separate environment. And this is a separate environment. And the last one is a separate environment as well. So we've got 1, 2, 3, 4, 5 different environments. It's decided to crash again. So this is not going well. I'll give it a second because it did fix itself before. Chance? Has it?
Yeah, it's still there.
Well, I was thinking if you try sharing your screen or just a random screen, then if I do it backwards, then it'll take it offline. It might fix itself.
Okay, hold on.
Try that because I think you're still the host, aren't you?
Yeah, I'll share my screen. Let's just put the Slido. Can you see that?
I can't see anything because it's not working on mine. Hang on. Let me try closing this. Really sorry about this. I was going to suggest we can just share the PowerPoint on your thing instead.
Okay.
And then
it says it's back on yours now.
Is it? It's still just.
Yeah.
It's just black boxes on mine. Nothing's really working.
Okay, that's fine. I will share the screen then. Hold on.
This is the first time.
It's quite annoying, isn't it?
Oh, I think Rehan's fully frozen now.
Oh no.
Okay. I don't know whether it's the internet connection from his side.
I think so. Sorry guys, there's just a few technical issues that we can't avoid. Okay, I'm just going to find his slide. I don't know if Rehaan is still there. Oh. So sorry guys. Okay, I'm just going to share my screen now so that you can see the slides. And we're just trying to get Rehaan to come back in, that's all. Link again. Okay. All right, guys, so we're just going to take a 2-minute break currently so that Rehaan can join back in. All right. One tab. There you go. So in the meantime, for the questions, can you explain mass spectrometry and infrared spectra after the past paper question, please? I will get Rehaan to answer that question for you when he does his Q&A. And then, do the free radical dot ever go to CH3 at the end since the one hydrogen was lost? But in the PowerPoint is at the front like this. So usually, if I'm not mistaken, the dot should go to the carbon at the back. But to be clear, I'm going to ask Rehaan to answer that as well. Try again. Okay. So sorry guys, we're just gonna have Rehaan just joining into the call again, and he'll be back soon. Sorry guys, so while we're just waiting for Rehaan to enter back into the call, I'd just like to give a shout out to our sponsors. So In2MedSchool is now being sponsored by MDU, Medify, and Medical Protection. And they have been very helpful in helping us grow our organization, as well as getting more recognition so that we can gain some more resources in order to get some finance in and basically offer the best that we can to you and all the other students involved as well. And in the meantime, just thank you very much to all of you here who are attending for this webinar as well. And Rehaan has just entered back into the call. It's just connecting. I'm just gonna give him a few minutes because he's still trying to connect. Okay, so sadly Rehan's having some problems with the Zoom, so I'm gonna take over from here and try my best using my A-level chemistry notes that I have in my head.
Well,
Okay,
do you want me
so
to just start the physical, and then if Rehaan gets back, you can always
No, I think we can just
Stop here.
we can finish this one now because I think Rehaan has to leave later as well. Yeah, it's okay. So we were talking about proton NMR, proton environments, right? So every single bond here, what I usually do that's easier is, write out there's a H bond here, there's a H bond here, and I'm just gonna annotate, draw. So I usually like to just draw it out that there are H bonds here and here, and this is what I do in basically all my exams, which is a lot easier to just annotate it through because over the exam you'll be rushing and everything. Okay, and then so you want to think about splitting patterns and the n+1 rule. I didn't really use n+1 rule, but some people do, and I can ask Rehaan later to explain more about that as well. Okay, so you've got the triplet, and then you've got a sextat, and you've got a pentat, then you've got a triplet again, and you have a singlet here. So, sorry, that's my fault. I was missing one more hydrogen here. Okay, so because I always remember that a carbon has 4 bonds. Okay, so what would this look like on a spectra? And I need to erase all of this. So now you can try it. And basically just get a piece of paper and just write it down. And just because due to time, we're just gonna quickly go through these. So these are all the hydrogen bonds on a proton NMR. And those two will be a triplet. So you get a doublet with 6 hydrogens, and then you then have a multiplet over here because there are 3 bonds where you are bonded to the carbon, and then there's only 1 more hydrogen that's missing that's bonded here. And then you got a doublet here, then you have a singlet here. So try and imagine like what would this look like on a spectra. And it's easy because you will have the data given to you as well that you will be able to see. So try and just remember it. Okay, and this is a question that you can do it through your own time for you to practice. Okay, we're just having Rehaan, who has just entered through the call. If you guys have any more questions about this, I think put it into the Slido and I'll get Rehaan to explain it more clearly because it's been a while since I've done proton NMR spectrums. Okay, so and this molecule, so you've got quite a few bonds here, and this was the mark scheme for the previous question that will help you. And then if you go through the mark scheme, it basically explains to you as to why each section has a number of hydrogens and what does it represent as well. Okay, and then now we're just going to hop onto organic synthesis, compound X. Okay, so compound X reacts with itself in the presence of another reagent to form compound Z. An intermediate compound, compound Y, is initially produced, which reacts in the presence of heat to form compound X, completing the synthesis below. Okay, so, oh, hi Rehaan.
Hi, sorry, right, that was something. Okay, how are we doing?
I think you should take over. It's been a while since I've done these.
Move to this. Okay, that's fine. Right. Okay, so we'll give you another minute to read this question. Can you hear me okay? Yeah, it's fine. You just carry on sharing the screen. Yeah, and I'll just do it through you.
Yeah.
Okay. Firstly, apologies for that, but this is technology, I guess. But yeah, I think it made it a bit more entertaining. So this is the question. So now, but on the organic synthesis part of it. Okay, so I think we'll do about 5 more minutes and then we'll move over to the next section. So this is one I've made. So compound X reacts with itself in the presence of another reagent to form compound Z. An intermediate compound called Y is produced. Try and think about what Y looks like. So this is a difficult question because effectively X is reacting with it. So you've got to think of the 2 functional groups reacting within the sort of the same chain. So if we look here, we've got a carboxylic acid, and this is actually an aldehyde on that carbon at the top. So the top carbon in the same chain, yeah, that's the what exactly. That is a aldehyde because it's a hydrogen there. So if we react a carboxylic acid with sort of the end product of the aldehyde, and we're getting an ester as Z, well, something must happen to the aldehyde, because how do we get esters? Alcohol and carboxylic acid. So Y must contain an alcohol. So if you go to the next slide, please, Chance. That's what Y looks like. So how do we go from aldehyde to alcohol? Well, we've got to reduce it with sodium tetrahydroborate. So the reduction of the aldehyde to the alcohol using NaBOH to form the esters, the final product, using heat, and water is obviously what's left, okay? So it's a very simple question, really. It's just asking how do you make an ester, which is done in an unfamiliar way, which is what makes it a bit more difficult. Okay, next question, please. Okay, so this is one I've made on barbituric acid. So I think we'll just talk through this one just because of time. So barbituric acid is a lethal compound. It's actually used in lethal injections, and I just think it has a really fun structure. So the production of barbituric acid is via an elimination reaction. So ideally we're removing something, probably water, between propandioic acid. So that's propane with 3 carbons and 2 carboxylic acids and another compound. This reaction, which is one molecule of barbituric acid and 2 molecules of another product, and write the synthesis in skeletal formula. So if we look at barbituric acid, okay, so propandioic acid is being used to make it. I wonder what else, possibly something involving nitrogen, who knows? And the likelihood is, yes, it's probably some form of amine. So next slide, please. And there we have it. So the propandioic acid, which is on the left, is going to react with this sort of diamide type thing. It's an elimination reaction because we're removing the water. So it's 1 molecule of propandioic acid and 1 molecule of the amide to then form 2 molecules of water and propandioic acid. Okay, next. Sorry, not propandioic, but barbituric acid next. Okay, so this is a synthesis thing. So there's 2 parts. This is in your booklet. So there's this, and the next slide is the second part of the synthesis. So I think I'll give you, well, I think this is probably best done in your own time, really. So we can go on to the next slide. We'll just have a look at these reactions, try and work them out, and then these are the answers for them. So this is the top part. So this will be in the answer booklets, and this is the bottom part. So I won't go through this right now, but this is another example of common synthesis they like to do. So again, it's just knowing your reactions inside out and then knowing how to change from one to the other. Next slide, please. Okay, great. So minus the technical difficulties, I think we managed to get there in the end. Again, very sorry about that. But thank you very much. And if you have any questions, please submit them through Slido. I think we have a few there. But yeah, I'll take a look as well. Do you want to read out some questions to me, Charms? Can you see them?
Sadly, I can't. I think they are.
I can. So the question round that we've got the most upvotes for is how do you recommend revising for chemistry, which is nice and broad, but I think a few hints and tips would be appreciated.
Mm-hmm. So with chemistry, like I said, there's 2 parts of chemistry. We've got the inorganic side and the organic side. I'll answer for the organic side because I'm sure Sophie will go through it. So the inorganic side. For organic chemistry specifically, the most important thing is that you understand the big picture and you understand why a reaction is happening rather than just learning the reaction. So again, you need to know how the synthesis happens. Why do we form water? Rather than just knowing I form water, if you're able to work out where the water's coming from in the reaction, like that barbituric acid question, you'll do so much better in the application questions. So again, it's all about why you why the reactions happen, how they reaction, and then knowing your whole flow chart as well. There's lots in the textbook. And in terms of actual revision, it's a good idea to make summary notes for all the different mechanisms. So on a piece of paper, write down all the stuff and then like stick them. So have like the aldehyde oxidation reactions, how to form an ester, amino acid reactions, ester reactions, acyl chloride reactions, all of them, different sheets of paper, and stick them on your wall. And just every morning before you go, whatever, to sixth form or just in the evening, have a read of those reactions and get them in your head. And then at the start of the day, write out those reactions, just know the most basic version of the reaction and then build on them. Okay. And then we've signposted some resources at the end, which Sophie will go through, of sort of textbooks and YouTube channels that are quite good. But past paper is also the most integral way to do really well in these. Okay, what other questions do we have? I think we've got some more specific questions.
Yeah, so it might need us to sort of skip back in a couple of slides. So it says, does the free radical dot ever go over to CH3 at the end since 1 hydrogen ion was lost? I don't think my syntax of that wasn't great. But in the PowerPoint,
can you repeat that? Sorry. Right. So, can we go to the slide, Charms, and then could you repeat the question there? I think it's right near the start. Just just do that.
So when we're discussing free radicals and we've got a CH3 with a star at the front.
Yeah.
Yeah. So do the free radicals ever go to the CH3 at the end? I think the question is because it's worded a bit funny. Whether the free radical goes to the end of the CH3, because in the PowerPoint it's the front.
Is it more a question of notation? So you wouldn't put the star at the end with the H because it's actually representing where the radical is in that molecule. So that electron is on the carbon atom. So you wouldn't put the star at the end. That's how I'm interpreting that question, is as more of a notation thing. Please, whoever wrote that, if I'm interpreting that wrong, put something in the chat. But yeah, that is why you would always put the star where the electron would be in that molecule. So in this case, it's the carbon, so it's in the front.
Yeah. So even because I asked the same question as well when I was doing my A-level chemistry, and they would say, my teacher said that you put it at a carbon because that's where, in terms of like position, when you draw the molecule, that's where the free radical would go to. So it's just all about the position, and you usually put it at the carbon and not at the hydrogen. And a hydrogen can't accept a free radical because it's already been, all its bonds is already bonded to carbon.
Yeah, it all comes down to sort of knowing your orbitals and your shells again. So you've got to just remember that hydrogen, it just hasn't got, think of it as it hasn't got the space to accept that electron. Carbon's where it's going to go.
Okay, I think Rehan's Zoom has just crashed again. So we will now move on to our next speaker for today, which is Sophie. I'm just going to stop sharing my screen and you can take over.
Oh, Sophie, sorry, I think you're muted.
There we go. For some reason, my mouse just didn't want to click on mute. So I'm just sitting there going, what's it doing? Technology today. Right, I'm hoping everyone can see these okay. So we'll just crack on because of time. Just to introduce myself, my name's Sophie. I am a year 4 medical student, so my chemistry was a little while ago, but I did do a chemistry degree before I started medicine, so this is a good revision for me. And I'm also the Norwich regional head. We go. So Rehan sort of already covered this, but what I've sort of focused on is the sort of topics that I see come up a lot in past papers, regardless of the exam board, but also the ones that I think tend to freak people out, which is the calculation questions. A lot of physical chemistry is tested with a lot of maths, unfortunately. And I know for a lot of people that don't do maths as an extra, it can be really freaky. So we're going to have lots of practice calculations. I'm going to take you through step-by-step sort of methods. Hopefully it'll be very helpful to you. But to get some maximum out of it, if you guys have a calculator on you or can get your calculator on computer, get that set up, so that would be good. So the topics I'm going to be talking about specifically are Born-Haber cycles, equilibrium constants, electropotentials in cells, transition metal complexes, and redox titrations. So we're saving the fun one for the last. So hopefully this will kind of ease you guys into a bit of physical and organic. I'm just going to move this so I can stop seeing myself and see my slides. So Born-Haber cycles, basically think of them as sort of extensions of Hess's law that you did last year. So it's about basically calculating enthalpy changes that you can't calculate directly. So I've got an example question here, and it just says complete the cycle by writing the missing symbols on the energy levels. And I'm going to give you a minute just to sort of maybe scribble something down. But effectively what you're trying to do is to go from this magnesium, this gaseous magnesium ion and this gaseous oxygen atom, get it, ionized magnesium, and again, an ion. So just think about what processes you need to do to get there. I'm afraid I won't be able to give you as much time as I like, just because technologists have made us a bit short on time. So what I will say is that you do have a choice here. So it's whether you decide to do, you know that you're going to have to ionize both of these atoms, but it's which one you do first, whether you do oxygen or magnesium. Now, to explain this, I'm going to sort of show the answer, because a lot of the times people mess up on Born-Haber cycles is just because they get the steps the wrong way around. So if I put all of the different you're going through, these are also just for, I'm not going to go through them, but these are some standard definitions that you will need to memorize. Basically, what the main question on this that I want to sort of get into, you guys, is why do we start with the magnesium and not the oxygen? So the reason why we do the first ionization energy for magnesium is because you've got to think that you're trying to give oxygen an electron to make it to reduce it to that oxygen anion, right? You can't do that if you do. You can't get an electron out from thin air. So that's why you always start, if you see a question like this and you have the option to make a cation, so something with a positive charge, always start by trying to get that cation first, because that gives you your electrons to then get to the next part. So yeah, hopefully that all made sense. A lot of these Born-Haber cycles is just practice, practice, practice. But the reason I put the steps is because, honestly, the first sort of 3 steps you can probably mix and match, but past that point, it's always in that order. So if you can remember that, you're now I mentioned Hess's law. So usually with Born-Haber cycles, they absolutely love putting in enthalpy of lattice formation for magnesium, oh, well, not magnesium, but any sort of lattice formation. What lattice formation enthalpy is the enthalpy change when you create 1 mole of an ionic sort of crystal lattice and from gaseous ions. So magnesium oxide in this case is an example. It's basically where you've got you're making 2 ions that have really strong electrostatic forces of attraction and whacking them together. So these are really exothermic reactions because you're creating quite a strong bond there. And this is usually how they'll test you on it. They'll just give you loads of numbers, which can look a bit daunting at first. But I go to here. Always go back with these sort of 2-part questions. Always just have a look to what you've just done, because this is actually telling you what you need to do. So effectively, you're trying to go from this magnesium, you're trying to work out this one here, so the magnesium 2+ ion and the oxygen 2- ion, and you're trying to create this magnesium oxide. But you can't actually measure enthalpy of lattice formation directly, even sort of in real life, you can't do it. It's only indirectly found. So you need to go from this magnesium 2+ ion and actually go backwards. So you go from there, all those steps that you've just worked out, down to the magnesium oxide the other way. I wish I could give you guys a bit more time to sort of work this out. But what I will say, I'll sort of speak on the slide so people who want to do it can have a bit of time to go through it. But the sort of key things you've got to remember are that where you have, where you're effectively going backwards, right? So if you're going against the direction of the arrow, so you're going away from the head of the arrow, not towards it, you are going to have to reverse the sign for that enthalpy change. So let's just take this magnesium 2+, which that very first arrow there is actually the, I think it's the 2nd electron infinity for oxygen. That's a plus sign, but I'm going backwards, so I'm going to have to reverse that. I'll show you the solution. It's going to look a bit yuck because it's got a lot of symbols in it, but just bear with me. So all of these H's are just the different enthalpy changes we've talked about. So the delta F is basically formation, then you've got your bond association energies, your first ionization, and then again your finally the lattice enthalpy. So this first one is just the equation representing Hess's law. So that LEH at the end is what we want. So we rearrange that. So we're then basically turning the signs round. And the things I put in red are basically the places that you can really mess up. So I'll explain. I've already mentioned why the signs are changing. So that's because we're going backwards on arrows. So whenever you change the direction of an arrow, you change the sign. The other thing I want to point out is the half here. So why am I halving the bond dissociation energy? Well, it's because if we look back at that, I only have one oxygen atom, or half, if you go right to the very beginning, half of an O2 atom. I haven't got a whole pair of oxygen atoms. So I am only doing half, technically, of the bond dissociation. So that's why I'm only putting half there. This is the thing that catches out a lot of people. So hopefully it won't catch out you guys now. If you take that sort of equation all the way through to the very end, what you should end up with, and by all means, if I haven't given you the right amount of time, do this in your own time, you should come up with minus 3,888 kJ mole to the minus 1. But one, I think if you find you end up with 4,100 and something, that's because you didn't halve the bond dissociation energy. That tends to be the most common mistake. And just, I've put that negative sign in red. What I would suggest to you whenever you have these sort of calculations is go back to your Born-Haber cycle and look at in this case, the lattice enthalpy that we were trying to calculate. It's a downward arrow. So I know that whatever I come up with has to be negative, because it's an exothermic reaction. So always double check your answer that way. It's just a good tip. So if we move on to the next sort of subject, which is equilibrium constants. And I just want to kind of remind you guys of Le Chatelier's, I can never say it, my French is so terrible, but Le Chatelier's principle. And this is the idea that whatever you do to a system in equilibrium, it's going to resist you, right? So it's going to try and stay as stable as possible. So I will, rather than explain it further, I'll let you have a read of this question. So it's looking at the formation of methanol. And I have methane gas reacting with water going to carbon monoxide and hydrogen gas. And then it's asking you what are the reasons, what would the effects of increasing the temperature and the pressure on the yield of the products be and on the rate of reaction. So what I want you to do when you have these questions is look at what the enthalpy change is for these reactions. So in this case, we've got a positive enthalpy change, and that will be quite important. So I'll let you just give you a minute to jot down very quick ideas. We'll just, sorry if I'm not giving you guys enough time, I'm just very conscious we've got a lot to get through. So let's talk about increasing temperature. So if we start with the yield, I know it's going to be a bigger yield because I'm shifting that equilibrium to the right. How do I know I'm doing that? It's because it's that enthalpy change that I mentioned. It's endothermic. So it's a positive enthalpy change, it's endothermic. So because of that, if I'm increasing the temperature, I'm actually shifting that equilibrium to the right. It's to resist it, it needs to make more energy, right? And that's by bond formation. So more product. And then this is a nice easy one with temperature, really. If you are increasing the temperature of something, you're 99% of the time going to increase the rate of reaction because you're increasing the amount of kinetic energy in that system. So what that means is you're going to basically, it's like giving all of your molecules coffee, right? You're giving them loads of energy and they're going to have more energy to be able to have these successful collisions to then react. So they're just bouncing all over the place. That's how I visualize it in my head. But that might be because I'm a medic, so I like my coffee. Now we're talking about increasing pressure. So in this case, we're going to shift the equilibrium to the left. Now to explain that, I'm just going to go back so that you can see. How I know that is because I'm looking at how many molecules, or moles I should say, of gas I've got on each side. The key thing here is they're all gaseous all gaseous molecules, but I have 3 lots of hydrogen gas on that side. I've got lots more molecules of gas on that right-hand side. As a result, to increasing the pressure will actually mean that I get less products. And with regards to rate of reaction, when you're increasing the pressure, again, you're looking at the gas moles, but basically you're trying to squeeze even more particles into a specific volume, right? So your size of your system isn't changing, but you're squishing more into it. And that energy means that they're all closer together. All these particles are closer together. They're going to be more likely to hit each other successfully. So again, we're increasing the rate of reaction here. I hope that all made sense. These sort of questions come up quite a lot, so it's quite a useful thing to be able to work out in your head. So the second part of this question is about equilibrium constants. We're getting gradually more wordy, so I hope you guys are okay with that. So let's have a look. Basically, what this question is asking us to do is find an expression for the equilibrium constant and then calculate a value for the equilibrium constant. So to give you a little bit of time, I will talk to you a little bit of blurb as you guys, if you guys want to have a go. So what is Kp? Kp is basically the expression, so it's an expression of the relationship between the amounts of specifically gas products and gas reactants. So hint, if it doesn't apply to this one, but if you've both seen it in previous questions before, if you see any other state symbol other than gas, you ignore it for Kp. Kp is only concerned with anything that's in a gas form. So you can just cut those right out. And again, it's for specific temperatures, specific pressures. I'm going to whiz through it. I'm sorry, I know you guys haven't had a lot, but we'll go step by step so you can kind of have a bit of time to get ahead of me if you want to. So whenever you have a question that asks you to come up with an equation or an expression, my advice to you is to always start with that bit. Always start by coming up with an expression or equation, because inevitably you're going to use those bits later on and they give you marks. Most of the time it can be up to half the marks. So just get that bit in and you'll be flying. So this just shows you how we would come up with a Kp expression. And in this case, so the P is showing that we need to know the partial pressure of the gases that we're looking at. And then the stoichiometry of the action, which is how many, and when I say stoichiometry, I mean what the numbers are in front of the molecules. So I have one of this molecule, two of the other molecule, for example. So that's your ABCs. And then they become indices. So they go sort of, I'll show you actually, it's easier. If you've done it, this is what you will end up with. So we've got the partial pressure for methanol, then partial pressure for carbon monoxide, and it's multiplied by the partial pressure for hydrogen. And because that hydrogen, I had 2 moles of that 2 then goes up to the top right. Hopefully that makes sense. So now we have that expression, we need to start doing some calculations. So this equation in blue, honestly, I'm not sure. I don't think they actually do provide this for you. It depends on the exam board you do, but I don't think it would be a bad idea to memorize this. So we're looking at partial pressures, total pressure, and mole fraction. Now, we haven't been given the mole fraction, so we need to work that out in this question. So I talked about stoichiometry. This is what you need to do, is work out basically how much of your reactant have you got compared to your product when it's at equilibrium. Now, the question very kindly gives us a lot of that. So it tells us that we have 62.8 moles of sample of the first reactant, carbon monoxide. And then it tells us that at equilibrium, we then have 26.2 moles of methanol. So if we go back to try and calculating the moles of the reactants at equilibrium, we know that we started with 62, but 26.2 of that has been converted to the product already at equilibrium. So we've got to take that away. Same principle goes for your hydrogen gas. Apart from in the case of hydrogen, we know that there was 2 lots of hydrogen to the methanol. Now that's important because obviously I've used twice the amount of hydrogen to make just, one of the methanol. That means that I'm going to have to times that 26.2 by 2. This is something that catches a lot of people out. So just always double check, look at what's in front of those molecules, what numbers you see. And then finally, we're going to need to work out, to get a fraction, we're going to need to work out what the total number of moles in the whole system of all those substances are when we're at equilibrium. And we've worked all the bits we need out for that. So we know that there's 36.6 of CO, there's 93.3 of hydrogen, and there is 26.2 of your product. So altogether, that is 156.4. This looks horrible, but trust me, once you've got that bit, it's like the easiest bit. This is just plugging it into the Kp expression that you've already worked out. So the 9.5 is the total pressure. So we had that equation, partial pressure equals mole fraction times by total pressure. So there are our mole fractions we've just worked out. We're timesing it by total pressure, and we've plugged it into the equation. So that 26.2 at the top, that's your reactant. Then you've got your, your product, then your reactants at the bottom, and we've squared that, the one that represents the hydrogen. We've done a lot of sort of, bringing it down to something nice. And before I give the answer, I want to just have a quick word on units. So this is where a lot of people get confused, I think, is what units should I give this? And a lot of the time they do ask you specifically to give the units. So this question told us that the total pressure was in MPa. So that's your starting point. Now, the units of Kp depend on the stoichiometry, again, of the equation. So how many moles I've got of everything. You, again, just sub it into your Kp expression. So I've got 1 mole of my product, which goes on the top, but then I've got 3 moles total of my reactants. And basically they cancel each other out. So that MPa cancels 1 MPa out, but then I've got 1 over MPa2. So it's going to become MPa minus 2. That is then your answer to that question. My advice, guys, is you'll get the worksheet, just work through it all, and once you've got steps in your head, you'll be fine. I'm going to give you a bit of break for calculations for a minute or two, and we're just going to talk about electrode potentials. And it just gives me a little time to check how I'm doing on time. Okay, 15 minutes. So we're going to whiz, I'm afraid, guys. So first question is, which element or ion in the table is the strongest oxidizing agent? And then I've got a question about explaining why copper doesn't dissolve in a strong acid such as hydrochloric, but why does it dissolve in nitric acid? So to explain this, chlorine gas is the most strongest oxidizing agent in this group. Why? Because it's got the most positive electrode potential. And you've got to remember that electrode potential is basically it's trying to represent how willing an atom or an ion is to accept an electron. So that chlorine gas is actually really happy to just accept those electrons in, because it's a halogen, right? It's got that space for that electron in its outer shell. So that question comes up a lot, is just recognizing that if you have a really, really positive electrode potential, that's going to be a good oxidizing agent. Comes up a lot. And then this question about why copper metal. This catches a lot of people out. So basically, it won't dissolve in hydrochloric acid because I put the bits here. When you basically put these two equations together, so effectively what you're trying to do is oxidize the copper using the reduction of hydrogen. But the problem is when you do that, you actually end up with a negative electrode potential. Whenever you're getting a negative electrode potential like that, the reaction won't go. If there's not enough energy in the system, it just won't do it. It's very stubborn. But why does it work in nitric acid, which actually isn't as strong an acid? And what I would suggest to you guys is just go back and look over what strong acid is compared to Bronsted-Lowry acids. It's another one of those things you need to memorize, but it'll make a lot more sense when you look at that. Now, what we're coupling here is different, but actually the reduction of nitric acid to nitric oxide gas is actually gives enough energy for the reaction to then oxidize copper. So what I would suggest when you get questions like this is look at the half equations, put them together, and then see, what sort of thing you come up with at the end, what number, was it positive or negative? In this case, it's positive, so the reaction will go. And I think just worth mentioning is that sometimes you have to reverse the way the reaction is going. So in this case, that's what we did with that nitrous oxide ion there. So it actually became then minus 26. There we go. Oh no, sorry, minus 34. We reversed the copper. So that's why that works. This is quite a basic question in the sense of I've seen a lot of questions where it asks you to know how to write a conventional representation for a cell. Once you know how it works, you could do it for anything. So I just want to make sure we've covered that for you guys. and conditions, that's just something to memorize. So I haven't included much memory stuff, but this is quite an important one. So we'll start with the conditions because that's actually lovely and easy. It's just, I won't even read them. Whenever you have a standard conditions or standard electrode potential, that's what you need to think is those 4 things. Talking about this conventional representation, what does it mean? And how do you work it out? So the first thing you've got to know is these vertical lines, they represent phase boundaries. What I mean by that is they basically separate species of a different state. So that platinum is a solid, the H2 is a gas. So every time you change in state or changing species, you put a line between. When you've got that double line, that's because that's where the salt bridge is. So that's what represents that. And then it really is as simple as just knowing that your anode, which is where your oxidation takes place, is on the left-hand side, and your cathode, which is where reduction takes place, is on the right. Now, I know in this case that the Ag and A plus is going to be on the right because I'm going from Ag plus to Ag, or rather Ag to Ag plus, sorry. So I know that that's got to be my cathode. And then the P2 just comes from knowing what your standard, I think it's called a galvanic cell, they call it, what is in that. So it's always a inert platinum electrode in hydrogen gas with hydrochloric acid, which is your source of H+. And then hopefully, just to give your brains a little bit of a break, we've got some complexes, true or false. I'm sorry, I'm not going to have a chance to give you guys the time to kind of run through them. So we're going to talk through them, but you'll get the copy so you can do it in your own time again and just double check your knowledge on it. So first one, platinum in this compound has a coordination number of 4, is a tetrahedral complex with bond angles of 90 degrees. That's false. The reason why is because platinum doesn't like tetrahedral complexes, doesn't do it. It only does square planar. So if you have nickel or platinum, it's going to be a square planar complex. It's just something to remember, honestly. But the rest of it is true. So in a square planar complex, you would have a coordination number of 4, i.e. the platinum, which is your central metal ion, has 4 coordinate bonds to, in this case, 2 of the NH3 ions and 2 chloride atoms. And the bond angles in a square planar would be 90 degrees. So silver in this complex has a coordination number of 2, and it's a linear complex with bond angles of 180. That's true. Silver is always in a linear complex, and bond angles, nice and easy for that one. Then we've got copper. It has a coordination, in this complex has a coordination number of 4. It's tetrahedral with bond angles of 109.5. This is again true. So again, you've got your, because it's not platinum or nickel, most metals like a tetrahedral complex when they have 4 ligands, and you can work it out, but honestly, I think that just remembering that you have 109.5 in a tetrahedral complex, it's not too bad. And I hate memorizing things, so hopefully that's not too much. I know you guys have got a lot to remember. So then we've got chromium in this complex has a coordination number of 3. It's not a tetrahedral complex with bond angles of 90 degrees. This is false. The reason why is because although there are 3 ligands in this complex, the coordination number is 6, not 3. The reason being that this is a classic bidentate ligand. Now, even if you have a bidentate ligand, you're looking at how many coordination bonds, so coordinate bonds they form. So in this case, this ligand will form 2 bonds each. So then it's 3 times 2 gives you 6. And then anything with coordination number of 6, think octahedral complex, and octahedral, like square planar, the bond angles are 90 degrees. And then finally, this is a mean one, but I thought it was mean, but I have seen it come up, and it's specifically on the shape of a ligand. I'm not going to go into too much detail on it because honestly, I didn't see this come up till I actually did my degree. But basically, you have an amide ion, and we're saying it has a bent shape with bond angles of 104.5, which is just slightly less than that tetrahedral. If you get something like this, the reason why is because you have in this ion, you actually have 2 lone pairs. Lone pairs repel each other a hell of a lot more than they will repel a bonded pair of electrons. That's why you have a slightly less. I think it's one of those things. I wouldn't prioritize memorizing it, but because I've seen it come up, if you fancy being challenging and you want to get that A star, it's worth knowing. And I just want to also take the opportunity to talk about isomerism here, because this is often tested in, they love testing this in the inorganic complexes section. So my summary guide to isomerism, as far as this goes, is basically you've got two rules. If you're thinking you have an octahedral complex and they have 4 of one ligand and 2 of another, or you have a square planar complex, so like your cisplatin, which has 2 of one ligand, 2 of another, think cis-trans. And what is cis-trans? Basically, it's where you have bonds that are restricted, you can't rotate them. So you end up basically having 2 different versions of a molecule that you can't, you can't rotate the bonds to sort of create each other. So the rules are, if it's cis, it's because in a complex, the 2 sort of like groups that are high priority, so in this case the Cl, they're at 90 degrees to each other. Basically, they're not opposite each other. If they're opposite each other, as is in this right-hand side, then it's going to be a trans isomer. You may also see this, depending on what exam board you're doing, they sometimes call this easy isomerism. So yeah, hopefully that still relates to you guys, but just if you see easy, hopefully that makes more sense if you didn't get the cis-trans bit. Optical isomerism, the rule is if you have an octahedral complex with 2 bidentate ligands. Unfortunately, it is a lot more complicated than this, but as far as you need to go for A level, this really is the rule. So if you see that, if they give you a complex like that and you're like really stuck, you don't know, inevitably it's going to be optical isomerism, because you're creating 2 mirror images. It doesn't matter how much you rotate this molecule, that you can basically put them on top of each other, and they're called I think the technical term is non-superimposable images. It might be something that you need to memorize as that phrase. But those are the 2 forms of isomerism. Okay, this is the last question. I'm just having a look at time. We're going to whiz through it. I'm going to try and whiz through it in a couple of minutes. So I'm sorry, I'm not going to give you a relative amount of time, but I'll take you through a step-by-step approach. If your first reaction to this question is this, you're not alone. I was like this is horrible. These wordy questions are the ones they never do at the end of the exam to basically separate your A's from your A stars. It's mean. But I'm going to take you through a step-by-step approach, which when you have redox titrations, it works with pretty much all of them. Okay. As I said before, if it asks you to make an equation, or even if it doesn't, to be honest, make the equation, because I promise you it will help you. It just gives you, inevitably will give you some marks, even if you're very, very stuck. So let's have a look at the equations for this. First of all, we know that we have this VO2 plus ion, and it's going to give this V2 plus ion. And in this case, it's being reduced because this, hopefully you guys are happy with your oxidation states. But you've got this, these minus, so the oxygen has -2. So then we know that that V is +5 in that species. So when you sort of balance it all out, that is what you will get. Again, if you do this in your own time, I promise you will get that. So the second half equation, it's told us that zinc is basically being oxidized from 0 to 2. So it's a nice simple one. Then we're putting them all together, and that is what you will get. So step 1, whenever you get anything of this, inevitably you're going to need to calculate the moles. In redox titrations, you will be given one species. Often the time it is this manganate or magnesium. Permanganate ions, I think is the classic that you guys will learn about. But you will have, even if it's not that, you will have one species that you know the concentration for. So always start with that one and calculate how many moles of whatever you know the concentration for has reacted. So that is given from this little section of all that blurb here. And it's as simple as plugging it into that basic moles equals concentration times volume equation. Little tip, they're normally really mean and they'll give stuff for titrations in centimeters cubed, which is just so cruel, unnecessarily cruel. So always convert that to liters or decimeters squared, or decimeters cubed, if that's what you're used to working with. So in other words, you've got to divide it by 1,000. This is what you should get if you did that. You've got to work out your mole ratio. And again, it might be permanganate, it might just be a completely weird off the rocker species you've never heard of, but you'll know the concentration for it. And to do that, we need another equation. I'm going to just whiz through that. So in this case, you're basically going from your, when you read the blurb again, you'll see it's a separate reaction that happens. But you're basically going to create this V5 ion. It sort of was before what we did with the equations. When you cancel all of that out, all your electrons and all of your waters and things, you'll end up with this. The reason why this is important is that because it tells me that I have 3 permanganate ions for every 5 of those VO2 plus ions. So that mole ratio is going to be 3 to 5. Why is this important? Well, when I'm trying to work out how many moles of metal reacted, I can use that ratio. So I know that it's 5/3, if you like, of the MnO4, which I have the 7.7 is my number of moles for that. So then when I times that by 5/3, if you like, that's what I get. Then you've got to, and this is actually the last step. Once you've got the moles, you're actually, you're flying. But this is sometimes the bit which catches people out. You get all of these calculations. It's like, ugh. It's just that mass equals moles times atomic mass, right? You should be given, if you don't get a periodic table, that's cruel. I'm 99% sure you'll be given a periodic table, so you will have these, you won't need to remember all of your atoms, atomic masses. Just basically, I'll take that, moles that I've worked out, I'll times it by the atomic mass of vanadium in this case, and that gives me my 0.0653 grams. Really important, double check what is the question asking you to give your answer as. In this case, it wants it percentage by mass. So to find the percentage of vanadium in the original sample, it's told me that I started with 0.16. So I basically divide my answer by 0.16, times it by 100, and you get 40.8%. Now, I'm really sorry, guys, that was a really, really fast run through. But hopefully, when you get all the slides and you can just sort of look through all the steps, that step-by-step approach will help you no matter what question you get. And just as a hint, that stem of calculate percentage by mass, you're working with a redox titration. So first step, just find whatever reactant you know the concentration for. I know that we had a couple of questions on resources, so I'll quickly whiz through this. It's going to be biased to what I found useful, I'm afraid. But I would highly recommend to you guys, I personally am someone that likes working through past paper questions, because every time you make a mistake, you won't make the same mistake twice. I personally think there are loads of questions on the physics and maths tutor link that we've put here, and it's actually what I use to sort of revise going back to my chemistry days. So I would highly recommend that. And on the YouTube channels, me personally, I like Snap Revise. So I think it's pretty darn concise, and it also will tell you what exam board it's relevant to, which is helpful when you guys are all doing different ones. But I always found him quite good at explaining things. And that is it. So I will let the guys here or Shah just sort of go through these last feedback for me bits, but shall we have a look at some questions?
All right, so you just go to the next slide, Sophie.
Yep. There you go.
Okay, thank you very much, everyone, for sticking with us today. I know we had quite a few technical backtracks, which was really annoying, but it's unavoidable. So here is the link to our feedback form. If you could please fill it in so that we can get some feedback from you guys on what we could improve, what we could have done better, what you enjoy, and what you learn. You're able to get your certificate of attendance as well once you fill in the feedback form. And also be very helpful if you could please fill in a Google review. And it will take a few minutes because you have to wait for a while as it links you to Google Maps, and then it takes you to our site for you to put your feedback about In2MedSchool. And again, I would like to thank you, our sponsors, Medical Protection, MDU, and Medify, for sponsoring us as well. And if any further questions, please email us at this Gmail email address. I will be emailing out the mark scheme for the question booklet, and Rehaan will be helping to answer a few of the questions that were directed to him on his section as well. So I will send those out together within probably the next 2-3 days. The PowerPoint of the slides and the recording will be uploaded onto our website. And in a few weeks' time, we will then also release it on our YouTube channel as well. So just keep an eye out for that. And now we will head on to our Q&A session, and Thea will be taking over.
So just looking at the questions that have come in, we actually don't have all that many added on after Sophie's section, because you've done such a fab job of explaining it all.
I hope that's why, and it's not just a case of I scared you guys to death, but if you do have questions, feel free to email me, and I'm more than happy to answer afterwards, so that's cool.
So we've had a question about getting sent the PowerPoints, but I think Shams has just covered that in terms of the PowerPoints will go up on our websites. One of the questions, I don't know how feasible this is, but has just asked whether you could explain mass spectrometry and the IR spectra. I don't know whether you would have enough time or resources to do that.
I know, so I'm sorry, I didn't include it in here because I think it's something that's covered, if I'm right, in AS. So apologies that I didn't cover it here. I didn't know, you know, I'll take that in mind for if I do this again, that's something you guys like to cover. What I would suggest, because explaining a mass spectra would take quite a few minutes, and I think we were supposed to end at 5. So what I would suggest to you is go to physics and maths tutor. In fact, is it all right, Shah, if I share my screen, I might be able to just show where I would find it. Would that help? That might be the best way to answer the question, actually. This is what I would do with regards to mass spectra. So, and also it helps you guys with regards to navigating the website. So it's hopefully a win-win situation. So if I just take KQA as an example, mass spectra comes under physical chemistry. I'm sorry if I'm just telling you how to suck eggs and you already know that. I'm pretty sure it's physical 1. Mass spectra, here we go. Right, so just a guide to physics tutor for anyone that hasn't come across it. It's really good because it will give you questions specific to the different topics. So in this case, you've got specific calculations for mass spectrometry here. So if you clicked on that, that'll give you that. With regards to where would it be in the notes? I'm pretty sure it's an atomic structure, actually. Let me just have a look. I'm saying is have a look at this, go through this part, and also just YouTube revise mass spectrometry. Oh, hopefully that's it. Okay, there you go. So if I go, here we go. This will basically give you everything that you need to know. From sort of what mass spectrometry is, how you use it. I won't go through it now, obviously, for time, but at least now you know how to get to it. And basically, or different calculations. Like I think the ones that come up that I've seen quite a lot are working out the time of flight and also explaining a spectra. And this should show you how to do that. I'm sorry we don't have time to do it now, but hopefully that's given you somewhere to go.
So the only other question, which sort of ties into the question asked previously about recommendations for how to tackle revision for chemistry, is do you have a suggested method of remembering all the required equations that aren't provided on the sheet?
Yeah.
I think it's quite individual, isn't it?
It is. It's really individual, and I feel for you because memorizing stuff is not my forte. So like you're not alone is the first thing. I know that with regards to equations, if you're quite a visual person, the triangle, you know, the triangle diagrams you saw when you were like GCSE science, sounds really daft, but I tend to find if you're visual, like color code each one and you'll remember that. And then when you get to the exam, just draw out those triangles. Most of them come in that format where you have something times something equals something else. So for those ones, that helps if you're quite a visual person. If I was going to say, it's a tough because it's personal. That would be my personal thing, is color coding, because I am visual. If not, if you're like auditory, something that helps me, this is like a general thing. If you're someone that learns by listening a lot, record yourself on your phone, going through like saying, for example, partial pressure equals mole fraction times by total pressure. Just record it. And it sounds daft, but if you listen to that, particularly before you go to sleep, it'll stick in your mind. It sounds like a daft thing, but it's quite a good way to remember things. It just goes in your head if you keep repeating it. 2 options. I hope one of those helps you.
Okay, so that's actually the last question that we've got through on Slido. If anyone has any last ditch questions, feel free to send them in now. Otherwise, we'll, I think, wrap up here. So I'll give you 30 seconds just in case anyone. Oh, so there's just one come in saying, will there be a session on AS material?
I don't think we've got anything planned for AS because our next A-level revision event will be maths in the next upcoming 2 weeks, and after that we're gonna have a break of the then we're gonna move on to exploring like alternative pathways into medicine and other healthcare careers in medicine. So we're moving away from the revision side now. However, if you do look through on our resources on our website, you should be able to find some AS and A-level resources on there that has been created by our educations team.
Where can I get exam questions and past papers to practice?
Cool. I'll take that one because one maths tutor, like I've just shown you, they have loads. I can show you sort of roughly like how much they get if I just go energetics, right? These are all like past paper questions. So that's a really good course, first of all, and they do them. This is just for AQA, but you actually have them for every exam board. The other thing, I think there's something called MME, is it? Chemistry paper, which gives you the past papers for, yeah, there we go. So mathsmadeeasy.co.uk, and that gives you the past papers for I think just the last couple of years. So if we go AQA, and then you can see, so it's got like your question, answer, and I think it goes all the way back. AS included as well for whoever asked about AS resources. That's a good one. So for all 3 papers actually. So those are the 2 that I know of.
And I think probably just final question that we'll take, how do we revise transition metals?
Yeah, so transition metals, I've done a little bit with the inorganic complexes. So from what I understand, the things that I've seen come up a lot, shall we say, is first of all like the shapes of ions that we talked about. So basically knowing the stuff that I covered in the slides is a good start. You also have to know, with regards to things you have to memorize theory-wise, I think it's similar to when you did halogens and stuff last year. You have to know the trends as you go down a group. The other thing comes up a lot. I didn't cover the things which were in memory sort of theory-based, but I've seen electron configurations come up quite a lot for transition metals and things like experimental things like calorimetry. So just remember, the thing with transition metals, right, is that you have variable oxidation states, crucial thing, catalysis, crucial thing, and then so revise sort of those 2 bits, but then also with regards to transition metals, redox titrations comes into that. What else would I suggest? I think the thing is, when I talk about calorimetry, it's basically knowing that anything that has so a full 3D, the classic questions I see is if you have a full d orbital shell, it's colorless and you can't measure it by calorimetry. I've seen that come up a lot. Be able to write an electron configuration for a transition metal and know the trends, same way you did with the halogens and your group 2 elements. I think it's group 2. So I think hopefully that answers the question. But again, physics, maths tutor it. I stand by that.
Fab, that's great. Thank you so much for your time, Sophie, to take those questions at the end.
No worries. Hopefully it was helpful.
There's just one more question that said, can you cover 6.4 amino acids, proteins, and DNA?
I don't know whether we can keep going with the individual requests for topics. I think we end up going into a spiral of trying to cover everything, won't we?
We're here for years. But I was just, so what do they say? 6.1?
6.4.
6.4. What? Oh, it depends on the exam board, truthfully.
Yeah, I think it's best, whoever asked that question, it's best if you just check your exam, like,
yeah. I presume
requirements and look at the specification as well.
It sounds like something that comes up in that sounds like OCR to me. I may be wrong. What I would suggest, I can't go over it right now. If you have specific questions or you're really stuck on something, feel free to email. I'm happy for the guys to pass something on to me. But I would suggest first point of call, find out what exam board you're doing, then go on to physics and maths tutor as an example, look at the detailed notes. I'm 99% sure that will help you with whatever, the full lot. But if you look at something, you just go, I really just do not get this. Email through the slides that we said, and I'm more than happy to have a look for you. But I'm 99% sure that it'll help you.
Okay, and I think that is the end for the Q&A. And thank you, everyone. And we will now end the live. Thank you.